Thanks. I'm going to talk briefly about a small project we had at Abbott. The pharmaceutics people measure octanol water log P and log D, and they wanted a better method to calculate ahead of time to help them set up their experiments. They had collected a fair amount of data with which we could test programs that had not seen that data. So this was a collaborative effort. Bill Porter was the one that set it up. He ran some of the programs. The rest of us ran different programs that we knew how to run. So it was, well, we met about 4 times, pooled our results, and that was it. Okay. Oh, I can change it with this? Okay, thanks. All right, so Tautomers are dear to my heart, as maybe you know. And we first realized we wanted to throw out the compounds that could tautomerize because we thought that would just complicate interpreting the results. How would we handle it? And we thought probably the programs wouldn't do as well with Tautomers. And this just shows you roughly half of the compounds had no Tautomers. So that cut down the data set, and someday we'll go back and look at the other ones. Okay, so just to show you what Tautomers can do to the log D calculations, this is a different data set now. It's the Proudfoot data set of commercially available compounds. And I just took the molecules that Aceleris said had Tautomers and compared the calculation within a molecule, the different Tautomers of a molecule, and showed how much it could vary. So you see that, I want to make sure. The log P, about 3/4 of the compounds that the 2 Tautomers are within 1 log unit. Now 1 log unit, of course, is quite a bit in some terms. But when you add in the influence of ionization, you decrease the number of compounds for which the Tautomers have roughly the same predicted value. Okay, so that's basically why we didn't want to look at Tautomers to start with. Okay, okay, that was just how you did it. So this is, in a way, the bottom line. We ran all these programs, and then Bill Porter sat with Excel and did all kinds of magic things. And basically, the best programs had a standard error of fit of 1.2 log units. So this is really depressing to people who care about physical properties. You know, we ought to be able to do better than this. But anyway, so Chemaxon was almost as good as the best one. I can tell you that's Simulations Plus. The other vendors really fell down. Let's see, okay. So then we asked, well, we've got 2 predictions. We know none of the predictions are so good. Can we do something about combining them, or Bill did all this work? And the bottom line there is if we take the average of Simulations Plus and Chemaxon, we get a statistically significant better prediction. And so basically that is the conclusion that we came to, that we need 2 calculators in order to estimate octanol water log D, and still it's a log unit. Okay. We can do all kinds of ways of combining the numbers, but the best way is to just take the average of the 2. The simplest way is the average of the 2. And so we recommended that we implement this Tautomer screening for all Abbott compounds and not report a log D for those. Let the medicinal chemist or whoever figure out what to do. And then in our Seurat presentation of the data, we want to give a warning to people that this is not like calculating a molecular weight. This is calculating a property with an error of about a log unit. Okay, so after that, I got to thinking, okay, there are these two programs, they're both okay. Can we get any more by mining the data within them? Do they agree generally? Probably they don't agree exactly, or we wouldn't get a better prediction, but how close are they? And so I just have a few graphs to show you. So this is a plot now, is this what I'm doing? Yeah, of the calculated value with the two vendors and the experimental. And the red line is the ideal. And you see the scatter in both directions. It seems like maybe Chemaxon is more often a little lower, but you know, but it gives you an idea of, in a way, how depressing this is. It's kind of like docking, I guess. You know, we wish it were better. Okay, now this is a plot of the difference between the two predictions. So, say 1 log unit spread from no or 1 log unit spread, and then the calculated. And is there any relationship there? No. And then these are colored by which is the closer one. So, you know, sometimes Chemaxon is better, sometimes Simulations Plus is better. And then this is looking at the spread between the predictions. So the difference between the predictions. So most of the time, the difference is only about 1 log unit. But there are some compounds for which the difference is really quite large. And this is, okay, the measured log D along here in different intervals. How many compounds? So most of them are, you know, there are too many way up at this end. You know, like everybody else, we've got too many compounds that we shouldn't be making. But then it's colored by which one has the closer prediction. And again, you see they're kind of tied for which is better. Okay, now this is, you know, my spot fire graph. So if you don't like pie charts, close your eyes. Okay, so this row is now the absolute value of the difference between the predictions. So in these two, the predictions agree pretty well, and they're agreeing less and less well all the way here. And the coloring is how close now the deviation between the observed log D and the average prediction. And you see that there's really no relationship between how well the two agree and how well the average predicts. And the next slide basically says more or less the same thing. This now is the average value of the deviation of the observed and the average of the predictions. So these are good predictions, these are bad predictions, and they're colored by how different the two predictions are. Do I have it? So the conclusion is, we wish that we could calculate octanol water log D with greater than 1 log unit accuracy. Now, log D has both a pKa component and a log P component. But the pKa, often we're far enough away that slight changes in pKa aren't going to change it very much. But I guess I was surprised that the calculations were so bad of the good programs. So is it a failure of the way we transform observed data into our calculation? Is it a failure of how we're describing molecules? Is it a limitation in the original training sets of how we built the models? Or is it problems with the data used to develop the models? I'm not sure that the models were ever parameterized directly on log D, but more on log P and pKa. So the bottom line, if we only understood water, maybe we'd be farther ahead. So I'm ready for questions. I guess I should. What I should say is that log D has now become the favorite parameter around Abbott. I don't know if it's everywhere. For all the years that I talked about log P and octane water partition coefficient, now all of a sudden people think that's okay, but really we want the distribution coefficient of pH 7.4. And we really would love to have a really good method, and I don't know how we get it. So the alternative is to do a bunch of measurements, spend a lot of money, contaminate the environment with octanol.
Were all the methods benchmarked against the same data set? And if not, then is it really fair to compare them? Because if you have benchmarked against a particular data set, then the authors may have done arbitrary tweaks inside the program to recapitulate those known values. And so comparing them in that way would actually lead you to overestimate confidence in the method.
I don't know how the programs were developed. All I know is that the Abbott compounds they had not seen. And you know, these were all tested on these Abbott compounds. Now, there were some standards, you know, when they were setting up the log P measurements, they did some standards that maybe the vendors knew about, but the majority of them were Abbott compounds of some interest.
Just a short question. Did you accidentally made some comparison with the log P and the pKa separately, so how it correlated? So which was the reason of this
Oh, okay. I actually have another slide. I did not have log P because most of these were ionizable compounds, as is true in industry. Most of the compounds are ionizable. So I didn't have many log P measurements that we had made. But I do have one slide. We started out, we were going to also evaluate pKa. And Bill Porter's group had measured carefully, you know, with temperature control and all that good stuff, 124 compounds. The problem is that many of the compounds, he observed 1 pKa, but a program would come and give you 2 or 3 within kind of the range. And so when we started to compare all of the different pKa prediction programs, well, which number do you pick out as the best one that Chemaxon did? Which one is the best one that Abbott did? It's like we couldn't be fair. We couldn't decide how to say who was closer or what. I suspect Chemaxon did a better job, but
It did. Colleagues, John Manchester wrote a paper about pKa predictions, and Chemaxon didn't care about, so I invite you guys to take a look at it.
The problem we have, it really is that we don't necessarily know the ionization site in the molecule, and so we can't map the experimental back to what Chemaxon or EPIC or whatever program says. And so we said, well, maybe later this year we'll work on pKa. But, you know, looking at this, I suspect that Simulations Plus and Chemaxon will both do well because that's components of the program.
It seems like I just heard you say in a slightly different way that you can't reliably predict the biologically relevant form of a molecule at pH 7.4.
Oh, probably you can.
Well,
But, you know,
isn't that what
sometimes,
you just said, though?
sometimes it's 60-40.
Yeah.
Uh,
But you could take, but you could have a level playing field by making a single prediction for each molecule and then feeding them all to all the programs, which is what you must have done for your log D calculation.
For the log D, it's very simple. But for pKa, for one molecule, you get lots of numbers out. There can be overlapping pKa's, so they're microscopic pKa's, or they're sort of observed mixture pKa's. I mean, it's a mess. And these molecules often had, you know, several potential sites of ionization, but that were fairly close. So only one would ionize at any one time, but the other one does a little bit. And they really needed log D anyway.
Integrate over all what you're integrating.
You could.
So getting to a couple of questions out on your conclusion slide, do you have any sense for the experimental error? Are there replicates or enantiomers in the set? And then the other question is about whether you have an in-house model to compare it to that might tell you something about whether the chemical space of the Abbott molecules was not represented, you know, where your in-house model would have that representation.
We don't have enough molecules to do an internal one. There's an effort to do an HPLC method to do log D, and presumably that would be high throughput enough that we could get a model for it. In terms of the chemical space, I don't know, but this is the point, really, that we want to be able to use the calculation for the fancy new molecules that our medicinal chemists come up with, not with things that look like all the old stuff that we couldn't patent anyway. So these are quite tight numbers. Yeah, these are the pharmaceutics people, you know, so they have to write stuff for the FDA. So they have fairly tight error bars on it. The ones at high log D are a little more questionable because that was an extrapolation from an HPLC method and so on. But we didn't do much more than that.
I have 2 comments.
Okay.
Actually, you can train the method. So if you have measurements for given your compounds, then probably you don't have to take all the compounds, but I mean, in just a small percentage of the compounds, you can build a model and improve the performance of the predictions. And the other is that there is a pK, there is a similar work from Richter about pK prediction as a poster.
Okay. I guess I don't especially like this training idea because then the next molecules that come along are different. You know, it's a different project. It isn't like all Abbott molecules are so different from the ones that went into the training of the commercial models. It's that the new ones coming in, they're really different. You know, they're different targets, different, and so the claim is these are global models, that they should work. And I think we might fool ourselves with this training, although I know it's popular to be able to train your own.
You can validate your prediction. There's a way to see if it's useful or not.
Okay, thank you very much, Yvonne. Let's give her another round of applause.